Time-appropriate greetings everyone, and welcome back. In this video, we're going to learn how to perform a simple linear regression using Microsoft Excel. In particular, we're going to determine whether the fuel consumption of a car affects its CO2 emissions. 30 cars are sampled, and data on their fuel consumption, measured in liters per 100 kilometers, and their CO2 emissions, measured in grams per kilometers, are presented in this data table. In this data table, each car has its own row and fuel consumption and CO2 measurement. Before doing regression analysis on any data, we must first plot it to determine if the relationship appears to be linear. Remember that a regression analysis should only be performed on data that have a linear relationship. To plot this data, select all of the fuel consumption and CO2 data, including the column labels. In the ribbon, select the Insert tab. In Recommended Charts, go to XY Scatter and insert a scatter plot. Looking at the scatter plot, we notice that the X values go up, the Y values go up, and they appear to follow a linear relationship. Double-click the title and give this plot a more descriptive name. I'm going to go with Car Emissions versus Fuel Consumption. In the ribbon, ensure that you are in the Chart Design tab and click Add Chart Element and add axis titles to the primary horizontal and primary vertical axis. We're also going to add a line to this graph that follows the data. Click Add Chart Element, Trendline, Linear. Let's give the axes more descriptive names. The vertical axis I'm going to call CO2 emissions. The horizontal axis I'm going to call fuel consumption. To make this graph a little more readable, we're going to change the axis size. Notice that it starts at 0 and goes to 10, but our data only lives between 5.2 and 8.8. Select the axis labels and go over to the Format Axis box. Click the Axis Options button, Axis Options, and change the minimum of this axis to 5 and the maximum to 9. Notice that it's now a much more readable graph, and that the linear relationship is even more apparent. Let's move this graph over to the side. Since the data seems to closely follow the line, we expect a linear regression to do a good job describing this relationship. Looking at its graph, we also predict that the slope of the regression line is positive since the CO2 emissions appear to increase with fuel consumption. Let's find the equation of this line using Excel's built-in functions. The first built-in function is Excel's slope formula. Excel has a built-in formula for computing the slope of a regression line. This formula is aptly named slope. Note that Excel requires that the Y values are placed first and then the X values. Select all of the CO2 measurements for the Y variable. Do not include the column title this time. Comma. Then select all of the fuel consumptions for the X values. Known Y values, known X values. Close this parenthesis and hit enter, and we've computed the regression slope. The regression slope tells us when the fuel consumption goes up by 1, say from 5 to 6, how much do we predict the CO2 emissions will increase? In our case, it's about 30. Let's interpret this slope in full context. For each increase of 1 liter per 100 kilometers in fuel consumption, so when the X value increases by 1, we predict that a car's CO2 emissions will increase by about 29.9 grams per kilometer. Now let's find the intercept of this regression model. Again, Excel has a built-in function for finding the intercept of a model, and it's also called Intercept. Similar to slope, it requires that the Y values go first and then the X values. For the Y values, select all of the CO2 measurements, again, not including the data label. Comma, select all of the X values. Hit enter and the intercept is printed. The intercept is 1.07. The intercept is the predicted CO2 emissions for a car that consumes 0 liters per 100 kilometers. Clearly, since no car can consume 0 fuel, the interpretation of the intercept is not really meaningful in real life. It's strictly a mathematical interpretation. Putting these two together then, we get the equation of the regression line. CO2 emission can be predicted from fuel consumption by taking 1.07 and adding 29.9 times the fuel consumption. If we want to predict the CO2 emissions for a specific car, we take 1.07 and multiply 29.9 times its fuel consumption and add those together. This is the equation of the line that best fits these data. Now, we can use the correlation coefficient R and the coefficient of determination R squared to assess how good a fit this line is to these data. To calculate the correlation coefficient R, Excel has a built-in function called Pearson. It's called Pearson because the usual correlation that we compute is the Pearson correlation coefficient. The Pearson function takes two arrays, the x and y values that you want to relate. It doesn't matter which order you put the values in, but I'll be consistent and put the y values first. So let's select all of the y values, comma, all of the x values. The Pearson correlation is 0.967. This is very close to +1, so the relationship between CO2 emissions and fuel consumption is very strong. And since we looked at it in a scatter plot, we know it's also linear. We can interpret this in full context by mentioning the strength, sign, and linearity of this relationship. There is a very strong, linear, positive relationship between CO2 emissions and fuel consumption. Similarly, we can compute the coefficient of determination R squared. This can be computed either by squaring the correlation coefficient or by using Excel's built-in function RSQ, R squared. Like slope and intercept, it takes the y values first and the x values second. Select all of the y measurements, the CO2 measurements, comma, and then select all of the fuel consumption measurements. R squared is 0.935, or 93.5%. This tells me how much of the vertical variation observed in the CO2 emissions is explained by this regression, 93.5% of it. So 93.5% of the variation observed in the CO2 emissions is explained by the regression on the fuel consumption. On the whole, we'd say that this regression model is doing an excellent job of modeling CO2 emissions using fuel consumption. The correlation is very strong, and R squared is high. So finally, let's use this regression model to make some predictions. In the data table, add columns for prediction and residual. For the first car, we make the prediction using the regression line. We take the intercept, and we add the slope times this car's fuel consumption. Intercept plus slope times x value. Since we'll be autofilling this formula to all of the rows, and we don't want the reference to the slope or intercept to move, we need to add dollar signs to the row numbers in the references to fix them there. Hit enter, and we have a prediction for our first car. A car with 8.4 liters per 100 kilometers fuel consumption is predicted to have a CO2 emissions of 252.39. Autofill this formula to the rest of the cars by moving your cursor to the bottom right green square and double-clicking. We now have predictions for each car's CO2 emissions. Let us now compute the residuals to see how much we over or underestimated each car's CO2 emissions. The residual is computed by subtracting the CO2 prediction from the actual CO2 observation. Observation minus predicted. The residual for the first car is negative 4.39. That is, the observed was 4.39 less than the predicted. We predicted too much for this car, and that's reflected in the negative residual. Autofill this formula to the other rows. Notice that a positive residual, such as in car 6, means that the car had a higher CO2 emissions than predicted, 232 versus 225. So the linear regression model tells us for each car what its predicted CO2 is and how far off that prediction was from reality. Simple linear regression is a useful and widely applied method of modeling and forecasting. Using Excel to do a regression analysis is made simple using Excel's built-in functionality.